Hello everyone, thank you for watching this talk. My name is Jakub Bokšanský, I'm a development technology engineer at NVIDIA, and I will be presenting you our work on crafting a real-time path tracer for Minecraft RTX. This is a two-part talk where I start by giving you a high-level overview of Minecraft path tracer, and I will provide some insights into interesting implementation details. I will also cover implementation of our BRDFs, and final part will be spent discussing denoising techniques we are using in Minecraft. For the second part of the talk, Olive Wright will talk about irradiance cache and other topics in greater detail. So let's start by taking a look at the key features we wanted to implement in Minecraft RTX. We were aiming to get a fully path trace rendering, meaning all aspects of the image that we commonly refer to by terms such as reflections, global illumination, and others, will be ray traced. To get nice lighting, we wanted to have per pixel emissives, which essentially means we wanted to support emissive textures for all objects. This will give us lighting from Minecraft objects such as glowstones, lava, campfire, and others. And we also wanted to implement physically based materials for greater realism and to even make it possible to model some of the materials, for example, the metals. And finally, we wanted to implement ray trace volumetrics, which gives us nice effects such as God rays and volumetric fog. And we have added participating media, which essentially means that rays flying through water or glass are colorized based on light extinction within given object. So if we want to implement the path tracer and look at the algorithm, we can see that it is conceptually very simple. The pseudocode on this slide will actually give you most of the things mentioned on the previous slide, except for God rays and media extinction. But you still get reflections, soft shadows, and so on. However, it will be very noisy and probably will take quite a long time to converge into usable image. The key here is to find ways to extend and optimize this basic algorithm to get all the features we want, but without noise. So denoising will be an important aspect of real-time path tracer implementation. It is also necessary to adjust this basic algorithm so that it doesn't produce output that's inherently difficult to denoise. For example, images should not contain caustics, flickering lights, and so on. Other consideration is making it performant, and one way to do this is to restrict the number of rays we shoot. Easiest thing to do here is to break this recursive loop early after just one bounce of light for secondary rays and move it into temporal domain so that we will get multiple bounces of light over time. We will discuss this in greater detail later in this talk. So first, let's take a look at the diagram of how Minecraft RTX renderer is organized. It is a multipass renderer, and if I simplify, we essentially calculate each BRDF in a separate pass and combine results in a special final combined pass at the end of the frame. At the beginning of the frame, we have a primary pass that resolves the visibility of primary surfaces, for which we also use ray tracing, although a rasterization pass would be possible. This pass, however, doesn't do any shading, it just lays down the G-buffer for other passes to use, and as a small optimization, it also casts shadow rays towards the sun. Notice that each BRDF pass is followed by a denoising pass except for the refraction, which uses a fast path directly to final combine step. As the image suggests, we use 3 different denoisers, one for diffuse, specular, and sun shadows, each fine-tuned for its specific purpose, and we will describe each of these later in this talk. Important detail that diagram doesn't show is updating of the irradiance cache, a mechanism that caches radiance received and emitted per each phase. Oli will give more details about this in his part of the talk. I will just quickly mention that we use this mechanism to get more than one bounce of light by feeding the irradiance cache back into itself over time. So even when we cast rays which evaluate just one bounce of light within each frame, these rays use irradiance evaluated in previous frame for their updates. So each frame gives us one more bounce of light over time. Final thing to mention here is that effects such as particles and rain are still rasterized and mixed in the final image during post-processing. Here I have prepared some images to illustrate what primary pass outputs. These are the snapshots of few selected buffers. It is a fairly typical G-buffer setup with albedo, roughness, metalness, normals, etc. What's unusual is the noisy shadows buffer in the top right corner, because in the rasterization-based renderer, there would probably be a shadow map evaluated in separate paths. But now we can evaluate sun shadows using raycasts and store them in the buffer as they are viewed from the camera point of view, unlike the shadow map, which would be rasterized from the light position. The next pass we'll take a look at is the indirect diffuse BRDF pass. That's the pass calculating contribution of diffuse BRDF for secondary rays. This is sometimes referred to as global illumination, but we need to differentiate between diffuse and specular BRDFs, both of which technically contribute to global illumination, yet are separate passes in our implementation. The images are showing raw output of path tracer on the left and the denoised image on the right. For reference, final image is in the top right corner. Note that in these images, the light from torches is not so apparent in the left noisy image, but it is still there, and after denoising the image converges to what you see on the right. For this pass, we use Lambertian BRDF, although for primary rays we use Disney diffuse BRDF. This will be explained in detail later, but just shortly, the reason is that after denoising the difference is not very apparent for secondary rays, and Lambertian is simpler to evaluate and is not view dependent, so it's a little easier to denoise. We also set albedo to white before denoising and apply it later in the final combine step, so that the textured albedo wouldn't be blurred during denoising. We also use spherical harmonics to store this buffer, which also improves denoising quality, as the directional information is encoded directly in the light, and denoiser doesn't have to deal with geometry normals. Next is the specular BRDF pass, which works in a similar way, but we use the same BRDF as we use for primary rays, which is a GGX-based microfacet model. Albedo is also set to white prior to denoising, but we do not use spherical harmonics to store this buffer. Another difference is that we also store reflection distance for each pixel. This is the distance from camera to what you see in the reflection along the ray path, and it is necessary for denoiser to correctly reproject values from previous frame, because we have to reproject what is seen in the reflection, not the reflection itself. Following is the refraction pass, which gives us ability to see behind glass and water surfaces. We make a simplification here and ignore roughness of the surface, so we only allow for perfect refractions based on Snell's law. The primary ray is therefore simply redirected and follows its path until it hits something solid. We allow up to 8 bounces of light before this loop is terminated. We also apply light extinction based on traveled distance underwater to create a fog-like effect underwater. We also track the medium the ray is traveling through, and we apply correct refractive indices when the ray exits one medium and enters the other. This gives us the effect called total internal reflection, which happens under certain angles when light will not exit the object, but reflects back into it and becomes trapped inside, bouncing around, until it hits some surface under such angle that it is able to exit the object. You can see the result on this image, where player is looking from underwater up to the surface. This is called the Snell's window, which is a circular window in which you can see everything on the ground on the surface, the full hemisphere, but outside of this window you can see the reflection of what's underwater, due to the total internal reflection. And the last pass we'll mention evaluates volumetrics, which are pre-calculated for the camera point of view and stored in a 3D grid. They're applied in the final pass for each pixel based on the distance of the primary ray hit. Now we get to the final combine pass, where outputs of all passes mentioned so far are combined together to form the final image. Here, we calculate shading for direct light coming from the sun using denoised sun shadows. We also apply specular and diffuse indirect light, which also requires applying Fresnel term and albedo of the surface, because these are ignored before denoising. We mix in the noiseless refraction buffer and fetch volumetrics from the pre-calculated grid. That almost gives us the final image you can see on the screen. Only thing that follows is the stack of post-processing effects, such as bloom and tone mapping, and also mixing in of rasterized features such as rain into the image. As a final slide in this section, I'd like to show you the relative performance of individual passes which we've discussed. So we spend about 15% of the frame updating the irradiance cache and volumetrics. Then actual ray tracing takes about 40% of the frame. 8% of those are the primary rays, which also include sun shadow rays. And the thing to notice here is that the largest portion of the frame is spent on denoising. Denoising is and will be an integral part of path tracing-based renderers, and it is important to dedicate adequate time for their optimization and fine-tuning. And we can expect that denoising will be a big research topic in the foreseeable future. To demonstrate what will the image look like without it, here are a couple of pictures. One is without denoising, the other will be final image with denoising applied. You can notice that some parts of the image are still noiseless, but those are either emissive or perfectly smooth surfaces. But essentially all the other parts of the image require heavy denoising to get usable image. And this is what denoising gives us, and why it's worth spending almost half of the frame time on it. Now we get to the next section of the talk, where we discuss the implementation of material BRDFs we use in Minecraft RTX. The first BRDF we will discuss is the diffuse BRDF. As we've already mentioned, we use the BRDF called Disney Diffuse, also called Burley Diffuse, for shading direct light from the sun for primary rays. This BRDF is described in detail in the article called Physically Based Shading at Disney, so I'll not go into detail of it now. I'll just mention that it's suitable for our use case because it reacts to roughness and combines well with microfacet-based specular BRDF. And it preserves Fresnel reflections observed under grazing angles better. For indirect light, we use symbol Lambertian diffuse, which is not view-dependent, so it introduces smaller error when reprojecting from previous frames under camera movement. It doesn't react to roughness, but difference between Disney diffuse and Lambertian is less noticeable after heavy denoising, and we only use it for indirect light contribution. An advantage of using Lambertian is that it's very simple to evaluate, so if we look at the Lambertian BRDF formula, it's just the diffuse albedo divided by a constant pi. For Monte Carlo path tracing, we know that we have to divide BRDF results by PDF of sampling given ray direction. So we can pick our sampling function in such a way that its PDF will cancel out some of the terms in the formulas. A typical choice would be the cosine-weighted hemispherical sampling, because its PDF is a cosine of angle between normal and light vector divided by pi. So this cancels out the pi constant in our equations, but it introduces division by mentioned cosine. This, however, cancels out with multiplication by the same cosine in rendering equation, so the BRDF weight becomes just the diffuse albedo. And as we mentioned, we set albedo to pure white before denoising, so our diffuse BRDF becomes just the constant one. For the specular BRDF, we use a microfacet model with GGX distribution, which is widely used. The advantage is obviously that it reacts to roughness, renders Fresnel reflections, and we can set PBR material properties such as metalness. We use it for both direct light for primary rays and indirect light contributions. So we need a sampling function which will give us the ray direction for secondary rays based on material properties. And we also need a PDF of choosing the direction. We settled on using the sampling method based on distribution of visible normals, published by Eric Heitz in his paper called Important Sampling Microfacet-Based BSDFs Using the Distribution of Visible Normals. The PDF of this method is limited to 0 to 1 range, which helps to reduce the fireflies, and also the full source code for this method is provided in a supplemental paper sampling the GGX distribution of visible normals, also written by Eric Hates. An important question, especially for path tracing, is how to combine those two BRDFs in order to satisfy the energy conservation requirements. Especially, how to ensure that energy of light exiting the surface will never be higher than the energy of incident light. If this wasn't ensured, it could happen that our image would converge to something very bright, because we calculate path tracing with multiple bounces of light, and the energy would be getting higher and higher on every bounce. We achieve good energy conservation for our BRDFs simply by weighting diffuse term by 1 minus Fresnel term. The specular is already weighted by Fresnel, which is built into it, so we just sum up those two results to get final BRDF value. And in order to test how our combined material BRDF behaves with regards to energy conservation, we have implemented a thing called white furnace test in our path tracer. It's a very simple test, and I can recommend implementing it in all path tracing based renderers to examine BRDF energy conservation. It is a rendering of perfectly white sphere, illuminated by white light from all directions. So in case our BRDF was perfectly energy conserving, the sphere would have to disappear. But you can notice on our image that the sphere is still recognizable, and it gets darker on the borders. That means our BRDFs are losing more energy on surfaces viewed under grazing angles. This is, however, not a big problem, as the main goal for us was to ensure the energy is never increased. And for transmission, we use what we might call a no BTDF, because we ignore roughness for refracted rays and only redirect them based on Snell's law. This way we do not get any color changes for rays being transmitted through the object, so we rely on light extinction underwater to colorize the results by adjusting the ray's throughput based on distance traveled underwater. And for glass, we apply fixed light attenuation based on glass color. This attenuation is applied for each glass surface that we hit, but the distance between those hits is ignored, so it doesn't change color based on glass thickness. This is to ensure that results match what we see in the shadows cast by glass blocks. Because we use any hit shaders to evaluate semi-transparent shadows, we wouldn't be able to establish thickness of the glass for shadow rays, because any hit shader is executed in arbitrary order for the hits along the ray. That concludes the implementation of our materials. We will now take a look at some interesting implementation details of our path tracer. So every path tracer, even the simplest one we showed at the beginning of this talk, will have to solve a few issues that occur in every ray tracing based implementation. The first one we take a look at is the problem of self-intersections. These occur due to floating point precision errors when the ray reflected from the surface hits that very same surface again. Simplest solution is to set what is called the T-min distance to some small threshold. That will only allow the ray to register hits past that threshold, but in case it is too large, we will get light leaks and disconnected shadows. So for Minecraft, we're using more advanced method called a fast and robust method for avoiding self-intersection. It is described in the Ray Tracing Gems book, and it works by offsetting the ray origin away from the surface by the minimal necessary amount, so also the light leaks are minimized. It works best when ray origins are close to the center of the world space, and that works very well with Minecraft, because its world space is centered around camera, and the whole world, along with all the acceleration structures, moves around the player. Next method we will take a look at is the implementation of MIB mapping for ray hits. It is common to use the automatic MIB mapping present in the rasterization pipeline. However, it is not so straightforward to implement it in the ray tracing pipeline. And we cannot use the MIB level 0 all the time, because for rays we will get the same problems as we do for rasterization pipeline, meaning moire patterns, low performance, and so on. There are multiple ways to implement MIB mapping. We're using one described in the article called Texture Level of Detail Strategies for Real-Time Ray Tracing, again from the Ray Tracing Gems book. This method works by approximating the ray using a cone, which gets wider and wider as the ray gets longer. So we just have to track the width of this cone based on traveled distance. Idea is that the cone covers an area on the surface that it hits that the ray is seeing, and we should select MIP level to match that. This requires fine-tuning the parameters of the cone, such as the initial width, and mapping the cone width to MIP level. And to get some performance boost, this mapping can be different for primary and secondary rays. For example, so that the secondary rays are allowed to fetch from higher MIP levels sooner. Another implementation detail we will take a look at deals with limiting the amount of variance or noise that our path tracer outputs. To make the job of denoiser easier, we can make some adjustments to our materials so that image doesn't contain features such as caustics, which make denoising inherently more difficult. We achieve this by increasing material roughness for secondary rays. As you can notice in the comparison images on this slide, the strong specular highlight is not present in the image with adjusted roughness. However, that is preferable to possible flicker and fireflies that would occur without this adjustment. In our implementation, we use a simple formula to adjust the roughness. For diffuse, we just clamp it to at least 0.25, and for specular, we rescale it to higher range. However, more advanced approaches are possible, which minimize the adjustment needed to reduce fireflies, and I can recommend reading the paper called Path Space Regularization for Holistic and Robust Light Transport, if anyone is interested in more details. Final method in this section is about handling many lights for path tracing. Generally, there can be thousands and even tens of thousands of emissive objects placed in the Minecraft world. For example, torches you can see on this image. And it is not feasible to cast the shadow ray towards each of these light sources and evaluate it as direct light, because we could end up shooting tens of thousands of rays per pixel. We will not get into great details of our method as it is out of the scope for this talk, but I will outline the basic idea on the next slide. It is based on stochastic approach, where we randomly select one light per pixel for sampling, and we rely on denoising to smooth out the results. Our algorithm works by randomly picking up to n candidate lights for each pixel. We use the value of n equal to 8 in our implementation. Then we evaluate the contribution of each candidate light to the shaded point as if it wasn't in shadow, because we're not shooting shadow rays yet, so we do not know if it's visible or not. We build the CDF, the cumulative distribution function, for these candidates, and stochastically select one from the candidate list based on random number. So lights with higher contribution have higher chance of being sampled. Then we cast a shadow ray towards the selected light and store the shading result in the buffer for indirect diffuse and specular BRDFs, because these buffers will be denoised. And in the next part of the talk, I will be covering our denoising techniques. As was mentioned in the first part, we have 3 different denoisers, one for diffuse, one for specular, and one for sun shadows. Here we describe all 3. But before we start, let's take a quick look at the SVGF denoiser. Our diffuse and specular denoisers are based on it, so I will now quickly summarize how it works. More details can be found in the original paper called Spatiotemporal Variance Guided Filtering. And if I simplify, the SVGF denoiser has 2 parts, a temporal filter and a spatial filter. Temporal filter reprojects results from previous frame to accumulate it over time, but it also mixes in denoise results from the previous frame. This can be made optional, so we can either accumulate raw output of path tracer directly, or slightly denoise results from previous frame, for example from the first iteration of the spatial filter. Or we can combine those 2 approaches in some ratio. Then the spatial filtering applies a low-pass filter, which is repeated multiple times, taking output of previous iteration as the input for the next one. An important detail here is that the effective size of the spatial filter is derived from the variance present in the image, So SVGF keeps track of the amount of variance or noise in each pixel and applies more aggressive filtering where appropriate. You can see the visualized variance in the image on the left and the corresponding denoised image on the right. So for the diffuse buffer, we use customized SVGF, and the adjustment we've made is that we increased number of iterations of spatial filter to 6, but we made it smaller, only 3 by 3 pixels. This change makes the filter more friendly to memory caches, which improves performance. For the temporal filter, we accumulate results from previous frames from the first iteration of the spatial filter, not from direct output of the path tracer. And as mentioned in the first section of this talk, we use spherical harmonics to store this buffer and apply the surface albedo after denoising. And here is a couple of comparison images to show input of the path tracer and denoise result. Notice how the light from point lights in the middle of the image converges, despite it is not very apparent in the noisy image. And this is the same image as before, but after denoising. For specular BRDF, we use same modifications as for diffuse, but we reproject values from previous frame based on the reflection. That's why we have stored distance from camera to what is seen in the reflection when we calculated specular BRDF path. Essentially, we're reprojecting what is seen in the reflection rather than the reflection itself. If we didn't do this, we would get significant ghosting in the reflections, most noticeable on the surfaces which are almost perfectly smooth, but still have some non-zero roughness. And for the sun shadows, we have a specialized shadows denoiser, not based on SVGF. SVGF with our modifications causes some ghosting, especially when time of day changes and the shadows move rapidly. Therefore, we have implemented a denoiser which is much more aggressive in temporal domain, meaning it doesn't store a very long history. Also, the spatial filter has an anisotropic kernel to preserve hard contact shadows better. And you can notice the large shadows in these images. That is because sun in Minecraft is significantly larger than the real sun, so a high quality denoiser is necessary to get smooth results. And now we're getting to the last part of my talk, where I'd like to mention the reference path tracer that we've implemented in Minecraft RTX as a development tool. So once the basic DXR integration is done, meaning we can build acceleration structures for our geometry, evaluate materials, and run ray tracing shaders, it is very easy to implement the most basic path tracer, something like the pseudocode shown at the beginning of this talk. It can be done in single ray generation shader, along with some simple closest hit and miss shaders. But it should feature multiple bounces of light and evaluate full materials and lighting. This will give us high-quality reference image that we can use for comparisons with our in-game path tracer. We use simple temporal accumulation for denoising, so it takes longer for the image to converge, but there isn't any bias introduced by spatial filters in denoising. And this tool is also a great experimentation testbed for ray tracing. Also, it can be turned into the high-quality camera mode with polygonal apertures and bokeh to produce high-quality image in-game. These effects would be complex to implement using rasterization, but are almost trivial using path tracing. And that concludes first half of our talk on Minecraft RTX. Ollie Wright will now continue with his part.
Thank you, Jakob. My name is Ollie Wright. I'm a dev tech at NVIDIA, and I've been working on Minecraft with RTX. In this part of the talk, I'm going to be getting into a little more detail about what goes on in one of our render passes, in this case, the diffuse pass. I'll show you what we need in an ideal world to solve diffuse lighting, and I'll show you what we can actually get away with. We'll look at some interesting corners that we can cut, and show you how it affects the final image. And finally, we'll look at something called the irradiance cache and how that gives us multiple bounces of diffuse light. This is a nice, simple, final rendered image that we'll keep coming back to. It's a nearly enclosed concrete room. There's no illumination in the room, but there is a door to the left that is letting in some sunlight. And in the corner is one block of magenta wool. So what's going on that we might be interested in? Think about how to light a pixel in this area. We need to know about all the light falling into this pixel from all directions. So what does the world look like from down there? This is the kind of thing that we'd really like to know. The image on the right shows the hemisphere of light coming into that pixel that we're interested in shading. That's why this part of the wall is lit with some pink from the carpet. But the thing to try to keep in mind here is that this is the information we need to be able to shade just one pixel. And we don't just need to shade one pixel, we need that information for every single pixel in the image. But do we really need this much detail? And are there any shortcuts that we can take? It turns out for diffuse lighting, we don't really need a full, highly detailed image like this. Something more like this can actually be pretty good. And often, pixels that are nearby to each other will have similar lighting conditions, and often the lighting conditions won't be changing very much from frame to frame. So there must be something we can do with that, right? It turns out that by taking only a single light sample per pixel, and assuming that the light falling onto neighbouring pixels is similar, that we can produce pretty good results. You often see images like this when discussing ray tracing. I just wanted to take some time to explain what exactly is shown in this image. What we have here is a single light sample for each pixel. It's tempting to think that this is actually sparse data, that the bright pixels are the samples and the darker pixels are some background. But actually every pixel has one sample. We call these secondary rays. The primary rays are the ones going from the eye into the scene, and the secondary rays are then shot from the surface in different directions. Which direction to shoot the rays is a massive topic on its own, and one that I won't be going into here. For our purposes, which is diffuse lighting, let's just assume that we're shooting the rays in a random direction over the hemisphere of the surface that we're shading. The process of reusing the information between pixels that are close to each other, spatially and temporally, is called denoising, and I won't be going into any detail about that either. It's also important to note that for Minecraft, we're sampling indirect light only. Actually, that's everything except sunlight, which we handle separately. So if you look at this part of the wall, you can see it looks brighter than the floor in this image. That's because the sunlight is excluded. If we look back at the original image, you can see what I mean. The bright samples on the wall are actually coming from the bright patch on the floor. This is what diffuse global illumination is all about. And hopefully you can see that this image already demonstrates that we have multiple bounces of diffuse light. Parts of the pink wool floor are themselves receiving pink light from the wall. But the wall is only pink because it has sunlight bounced from the pink floor. This leads us on to the topic of shading level of detail and how it can help us to get a good image quickly. Because we don't think we need super high detail for the secondary rays, are there things that we can do to cut corners? There are easy things like normal mapping and detail mapping, etc. Let's look at some of the lower detail shading that we do in Minecraft and how it might be surprising. This is our final image again, and technically this could be thought of as our highest level of detail. We're shooting primary rays and secondary rays, and we have the full denoising chain. So this image has diffuse and specular and reflections and refractions. And this is what our next level of detail looks like. Don't worry too much about what it's for yet. Just know that it's cheaper and it has some obvious compromises. If you squint, it doesn't look too bad. So I'm going to be referring to this as high detail shading. And this is our lowest level of detail. It's very poor quality, flat shaded quads. It looks like it's straight from the 90s. If you squint really, really hard, it kind of doesn't look too bad. What could we possibly use this for? I'll be referring to this as low detail shading. So what would the image look like if we shaded our secondary rays using each of these two lower detail shading methods? Not the primary rays, the secondary rays, the ones that are shot from our random directions from the surface. Well, this is what the image looks like if we shaded all our secondary rays using the high detail method. It actually looks remarkably good. This high level of detail includes specular reflections, so we actually get a nice caustic reflection up on the far wall. And we can see a nice detail in the GI of the pink carpet against the wall. You can see where the shadow, where the sun shadow lights half of the carpet. So how about the really low detail shading? What happens when we shade all our secondary rays with this? Again, it's surprisingly good, but we can see problems now. If you take a look at the wall near the carpet, the detail in the GI is gone, because in the low detail shading, there just isn't enough detail there. So let's compare these two images. This is the expensive one, and this is the cheap one, the low detail. And most of the image looks absolutely fine in both versions. Let's look again. But the difference in cost is dramatic. So what we'd like to do is use the cheap, low quality shading when there's little difference, and the more expensive version when there is. So how do we do that? We often find it useful to think of rays as cones. When we're shooting a diffuse ray, for example, the amount of fine detail we need is quite low. So it would be nice if we could shoot a fat cone instead and get some kind of average of the radiance for the directions covered by the cone. But ray tracing is ray tracing. It's tracing rays. So we think of rays when we're ray tracing, but we think of cones when we're shading. The width of the cone at the hit point determines the level of shading, the level of detail of shading that we require. When we're tracing specular reflection rays, we use a heuristic to assign some cone angle according to the roughness of the surface that the ray is being launched from. So a reflection ray from a very smooth surface has a very narrow cone, but a reflection ray from a rough surface will have a fat cone. Jakob has already covered this a little in reference to the bitmap selection, but the same principle applies to other levels of detail, in this case, shading level of detail. So if we use a fat cone for our diffuse rays, and using the cone width at the hit point to select between the two different shading levels of detail, this is what we get. The white pixels are using the more expensive method, and the black pixels are using the super cheap method. Because with diffuse rays we're always using a fixed cone angle, the threshold effectively becomes a distance threshold, so it's really easy to select. Close hits use the more expensive methods, far hits use the cheaper methods. And we tuned the threshold to give a good balance between visual quality and performance. Now I'm going to jump back a little bit and talk about what exactly is going on in these two methods of shading the secondary rays. Why do they look vertexy and facey? It boils down to something we use called the irradiance cache. And this can be thought of as a light mapping technique. It's a mechanism that enables us to reduce the cost of our secondary ray shading, and it also gives us multiple bounces of diffuse GI. To shade a surface using our high detail method takes three parts. there is the cached approximation of incoming indirect diffuse irradiance. There's sunlight, and that requires shooting a shadow ray, and there is any emissive component from the surface itself, like glowstone. So the incoming irradiance cache is currently stored per vertex in Minecraft. We do have a different version that we're working on that's storing it in spherical harmonics. But right now, the vertex-based one is working okay. And it's the irradiance cache that provides the global illumination. It means we don't need to shoot tertiary rays. What happens when we shade using our low detail shading method? Here we're using a slightly different cache. This time it's a cache of outgoing irradiance from the surface. When we're looking up data from the cache, we're really asking it what the radiance is in the direction of the ray. But the shading model that we're using here is very simple and independent of view direction. So in this cache, the outgoing radiance is the same in all directions. So we call it the outgoing irradiance cache. The outgoing irradiance includes all of our lighting. So it includes sunlight, and it includes any self-emissivity from the surface. The result of this is that the final diffuse lighting result is what's stored in the cache. When we're using this cache to estimate the radiance coming from a particular direction, it's just a simple lookup from the primitive index. That makes this super cheap. This is what the data looks like in our current implementation of our incoming irradiance. The left side is the final image, and the right side is what the incoming irradiance cache looks like. It's stored per vertex that you can see. The updates for the irradiance cache are spread across many frames. We have a budget of so many vertices that we can update in a frame, and we always update that many vertices every frame. Each update shoots a single diffuse ray from the vertex, and the results are accumulated with a temporal filter. And as bad as this looks, it's very important to keep in mind that the left side of the image is using this cache for its lighting. Instabilities in the cache are smoothed out naturally by the denoising passes, and the fact that we're shooting a different ray direction for every pixel. And this is what our outgoing irradiance cache looks like. It's just a single color per face, and it's updated in a very similar way to the incoming irradiance cache. And because this cache stores the final results of the diffuse lighting, if you squint, it kind of looks like a final image. But it means the lookups are very, very cheap. This video demonstrates how the irradiance cache gives us multiple bounces. It's another white concrete room, this time with a bunch of end rods to illuminate one end of it, but there are a series of baffles in the room to block direct light. The diffuse albedo of the concrete is 85% linear, so we're not cheating by having 100% reflective concrete. And we've also locked out the exposure and disabled the tone mapping for this video. But I hope you can see there is still some light that makes it to the end room. So that was a quick dive into the kind of things we're doing in Minecraft with RTX for diffuse lighting. But there are lots of topics that we haven't covered here, like specular reflection, shading, and denoising. If you're interested in making PBR textures for Minecraft with RTX, I highly recommend the talk Creating Physically Based Materials for Minecraft with RTX. And if you're interested in real-time ray tracing in general, then I recommend the RTX Ray Tracing Best Practices talk also. Thank you for listening. I hope you have found this talk useful. And since you got this far, I'll leave you with a few screenshots.